Welcome back, learners. So we would continue into quantifying sustainability for process designs. In the previous lecture, we have spoken about how sustainability is an important factor in terms of that has to be considered while designing any systems. But the key embodiment there is to have um, how to define a metric or a mean to quantify the sustainability. So there are ways to say that your system is sustainable, but how do you quantify it? So in this particular session, we try to look forward on various frameworks by which you can quantify the sustainability by means of footprints assessment. So we look at various process networks, okay, and analyze them and try to see, can you quantify the footprint related to water, carbon, and so on and so forth. So once that is done, then you may integrate this quantified input while designing any system. That's the plan. So before we move on, we will start. We will recap everything again. The reference material for this particular lecture is fairly uh, comprehensive from the textbook by Professor Bhavik Bakshi on sustainable engineering. So we will mostly follow that particular text in for the material related to this particular session. So maybe before we look into the session topics, let's look at the some components that we have learned in the previous lecture, so that we can prime up ourselves. So we talked about sustainability and we talked about life cycle assessment. So the key aspect of life cycle assessment is that it is crucial for gauging the environmental impact of processes or products. But the problem is that there are various uncertainties that affects the actual calculation of life cycle assessment. These include parametric uncertainties, which basically due to the inconsistencies in the input data, because there are data is coming from diverse resources, there are various geographical differences, and there are technological contexts, and so on and so forth. The next is scenario uncertainty, which is coming from the system boundaries and functional units, and they affect the outcomes and interpretations of your life cycle analysis. And the third is the model uncertainty. The model uncertainty coming from the need to simplify any complex system to simple mathematical models. Your process system that you are dealing with is fairly complex in terms of its size and in structure. So, but for the analysis purpose, we actually look for a smaller subset or a smaller prototype, which we achieve through various assumptions. Okay, so once we assume certain quantities, then there are issues related to this assumption which help to simplify your process. So this is another case of uncertainty, and addressing all these uncertainties involves you can do various statistical analysis, sensitivity analysis, and scenario exploration to bolster the accuracy and reliability of LCA. So the next is validating LCA model against empirical data and comparing them alternative model. We can also help in mitigating the model uncertainty. So basically, LCA you will have to work. The inferences of the LCA has to be obtained by looking at the contents. Okay, so how the uncertainty affects its contents, and thereby we can get a transparent assessment for environmental trade-off. It's fine. So once we have this, now we can look at how do we. So this is all about in general life cycle assessment, sustainability, and sustainability quantification. Now let us look a simple case study wherein you have a process 1 and a process 2. Okay, in the process 1 you consume 50 liter of crude oil and you meaningfully produce 20 liters of fuel. In the second case, you use 2 liters of such fuel and produce an electricity worth 10 kilowatt hour. So this is, you may consider this is a process which is similar to petroleum refining, because the input going here is crude oil and you use them to produce the fuel. In this case, this is like any power generation process wherein this fuel is going inside and you are getting power as output, but both of them would generate footprints in terms of the environmental emissions. So in the first case, refining generate 2 kilogram of SO2 and 10 kilogram of CO2, while the electricity generation process, okay, due to possibly the improved efficiency and also you are only consuming less amount of fuel, would only resulting 0.1 kilogram of SO2 and 1 kilogram of CO2. So basically these two modules are typically you need to see or integrate them together to get your final product. So even though they might stand in different geographical locations, but you, so without fuel you will not be able to produce electricity, which essentially means that you will have to anyway resort for a fuel production scheme where you actually use a different feedstock or an inputs, for instance crude oil, to generate the fuel, and by means of that certain environmental emissions are occurred. So this, let's consider this and we will move on, and we would now try to generate a process network analysis uh, uh, for this system and looking at some possible replacements. So what we have to do in those contexts is, so we have to identify models of individual units, in this case the process 1 and process 2, and of course you have to use the data inventory from life cycle assessment databases. And for instance, if your emission, if you are interested in producing 1000 kilowatt hour of electricity. So mind that you have to actually, so the normal process is producing only 10 kilowatt hour of electricity. So what essentially means that you need to have a scaled version of process P2, scaled up version of process P2, and the process of course is involving your electricity generation and fuel production. So what you have to do is you have to scale up the process P2 by a factor of 100, then only it will give you a 1000 kilowatt hour of electricity. So as a result, you will have to also scale. So this is scaled by some X percentage, in which essentially means that you will have to scale the other one is also by n equal percentage. So which essentially means that, so you will have to look, so you will have to look for a 500 liters of crude oil. Okay, so 500 liters of crude oil here would result 200 liters. So it is 10, right? 200 liters of fuel, and this 200 liters. So when you multiply this 100 times, so this would be again 100 to become 200. So this is how it translates. So you require 1000 kilowatt hour electricity, which is essentially mean that you require 200 liters of fuel, which essentially mean that this output has to be 200 liters, since this has to be 500 liters. Fine, and a practical implication of that is this will now become 10 times more, each of them, right? So your input has become and input and output is also scaled up by a factor of 10. So this would result in 30 kilogram of SO2 and 200 kilogram of CO2. The above system, whatever we have discussed, is fairly simple. There is nothing complex about it. You have two process unit which are independently operating fine, and this analysis is fairly easy to calculate in any of the systems. But the real life systems are fairly complicated, and this required a most generalized strategy to analyze. So this analysis we could just do by means of certain hand calculation, but a real complex system may require a further steps for analysis. So let's move towards that generic analysis. Again, don't lose the big picture. So we are interested in quantifying sustainability of a process by means of footprints assessment. And once it is done, you can include your this metric in the process design. So every process unit, you could identify two sort of flows. One flow which is relating economics, one flow relating environment. Economic flows are typically generated by human activities, and they are valuable to the society and not directly discarded to the environment. For instance, fuel and electricity valued for your utility, and and of course this term as final demand, because this is the end consumption of the society. So once so economic flows would be consumed in the societal boundary itself. Now look at the environmental flow. So environmental flow, the key difference here is that it is from or to the environment, okay, and it actually cut across the system boundary. It would move across the system boundary. So from or to the environment, because the flow direction is from or to the environment, and include natural inputs and emission to the environment fairly the same. So for example, in the previous case, your crude oil is used as an input, and for sulfur dioxide and carbon dioxide as emissions. So crude oil is coming from where? It is coming from the environment by means of extracting it from an oil well. Okay, so it is a matter that is coming from environment. So in such, it's part of the environmental flow. But this crude oil is now going to the society, so it is cut across the society. And what is happening? And crude oil is used to generate, or as a result of the consumption of the crude oil, you see that emissions are generated. So the emissions are not also not limiting into the society, it is going back to the environment. So it is cutting across the society and the environment. So that's what it means. So now what we need to do is we need to figure out a mathematical framework, fairly simple. Like I'm saying, the framework has to be simple, the analysis can be complex. We need to have an analysis that helps you to characterize or model these complex interactions of this economic and environmental flow. So this is how the material balance or the energy balance come in. So this is where you also have to relate to some of the topics that you have learned in the initial part of the course, wherein you found to or computed the material energy balance of process flow sheets and so on and so forth. So this is how both of them do their handshake and try to connect with or try to join the connection. And once this is done, so we can actually identify the impacts of each process in a network, because something is being consumed, something is being sent to the society or boundary, and it is also going back to the environment. And this interaction actually helps you to identify the uh, process details, and this also facilitates optimization and sustainability assessment. This is what we are going to look at over here. So now let's how to do this mathematical framework. So let's again look at the process P1 and P2, 50 liters of crude to 20 liters of fuel with 2 kilogram of CO2 and 10 kilogram of 2 kilogram of SO2 and 10 kilogram of CO2 emissions. And process P2 again 2 liter is the input or consumption, and 10 kilowatt hour is the electricity produced, and 0.1 kilogram SO2 and 1 kilogram of CO2 is being generated. So now let's to characterize, let's define certain variables. So for instance, let's call F1, F2 are the economic flows of fuel and electricity. Fine. So in this case, these are the only material that is concerning the economic flow. And S1, S2 are the scaling factors or multipliers of P1 and P1, P2. Okay. Now, Ri is the total environmental flow of the ith component. Then we could just create what we call it as uh, what we call it as a technology matrix. So technology matrix would consist of the flow rates of the economic products from each module with inputs having a negative sign. Okay, so just to capture the directionality, input typically used a negative sign, and what we later get is an intervention matrix. So intervention matrix, in again there the negative sign indicates that the input indicates input, and positive sign indicate output. So we can see how we try to generate an intervention matrix and technology matrix. So look at here. So the input to this system. So let's say if you combining this entire process, 2 liters of fuel is going an input and 20 liter is being produced. So it would be 20 S1 minus 2 S2 is equivalent to the economic flow of fuel. Okay, there is no electricity here. Fine, it is going out as 10 kilowatt hour. It would be 10 S2 is equal to F2. And eventually you shall be able to write this in the form of a matrix. So 20, 2, 0, 10 and S1, S2 are, as I told, the scaling factors. Now you can scale how much ever you want, right? So this is the system, and if you wanted to scale it 10 times, you only need to plug in these numbers to get the corresponding value of F1 and F2. And this would result in the nice equation metric structure AS is equal to F. So now look at the environmental flows. So environmental flows, okay, so there is a crude oil that is going inside, it would 50 S1, and so there are two sources of emissions, 2 kilogram of S1 and 0.1 kilogram of S2, 10 kilogram of S1, and what you call 1 kilogram of 1 kilogram of S2. So you may write this again in the form of nice equations. So this is RSO2, this is RCO2, and now these would be your outputs in the environmental flow. So they comes into the right hand side, R crude, RSO2 and RCO2, minus 50, 0, 2, 0.1 and 10, 1. So this would be your environmental flow matrix, and this economic flow matrix would have a structure of AS is equal to R. S would be the common thing across both because they are the scaling factors. AS is equal to F and BS is equal to R. Fine. And for a specific consumption of products of society or fundamental demand F, the resource consumption and the emission can also be computed now by what? R is equal to, so you are BS, right? S, how do you get? B inverse A, so R is equal to B A inverse F. So here you compute the S from the inverse of this, okay, so which is A inverse F, and you plug in over here, B A inverse F would be the final resource consumption and emission quantity, which is relating your, in this context, it related to the crude, SO2 and CO2. So now move on. So now let's kind of, so okay, the example stands the same. So now you say that the final demand has is now 100 kilowatt hour and 100 liters of fuel. So this, then how do we do this now? Because the previously we did the same by means of hand calculation. Now that we have this matrix representation, equation matrix representation, let us see how do we do this. So we are sure now. So your F1 and F2 is which is representing your fuel and energy, so which is 100 liters and 100 kilowatt hour. So we can easily write 20 S1 minus 2 S2 is equal to 100, 10 S2 is equal to 100, and in the other cases, so this would eventually solving of this equation you can just replace, and we will get S1 is equal to 6 and S2 is equal to 10. So once you have S1 and S2, we may be able to plug in back over here, okay, and this would result in RCRD equal to minus 300 L, RCO2 is equal to 13 kilogram and RCO2 is equal to 70 kilogram. Fine. So now how do we we use this calculation by means of resource consumption matrix. So we have the matrices available. What we need to compute is this particular relations, which is B A inverse F. So how do you compute B A inverse F? This is your B matrix, which is coming from the previous thing, and we have to compute the A inverse, and F is 100, 100. This would eventually result minus 300, 13 and 70, which is the same as of this. So this is why simply using the variable aggregation and use the principle of matrices and linear equation solving, we will be able to quickly compute this. This is of course the step-wise calculation, and we have also looked at it before without looking into the detail. by means of only what you call by means of only looking at in a heuristic framework initially at this point. Reset, yeah. So it's at this point. So what I'm trying to say is, so now this is a generic network. So you don't have to do any you don't have to do any heuristical steps to calculate. You will have to isolate the economic flows, environmental flows, right? Compute the technology matrix, intervention matrix, and just solve them in one shot. So now look at some more nitty-gritties or nuances that is related to. So see, we have not computed the sustainability assessment by means of footprints. This is basically to analyze the resource consumption R. So now from this resource consumption, we should go to a mechanism that helps you to characterize the emissions. Eventually the footprints. So this is first part is of course computing the resource consumption, and we are successful at this point of time. So now let's look at how to characterize into measurable environmental impact. So flows are now available with you. So now we should characterize this environmental flow to measurable environmental impacts. So this will help or facilitate the comparison of different environmental impact by converting to a common unit. So eventually how do you, so we need to have a common benchmark to understand how these things are affecting. So it's important that we convert them to a common unit before we do any sort of inferences. So for example, so nitrogen dioxide emissions are converted into sulfur dioxide equivalents to measure the acidification potential. So, so typically the acidification potential is measured in terms of CO2, and NO2 is another gas emission, but you will have to convert that in the form of SO2 and eventually in terms of acidification potential. For instance, the way it works is the conversion factor of NO2 to SO2 is equivalent to 0.7 kilogram of SO2 equivalent per kilogram of NO2. So this is what we call it as the characterization or of factors. So you will have to characterize something to a common footing, so that it is easy to visualize. So if there are multiple such independent metric to compare, okay, it will be very difficult to make any sense out of it, because all of them would be having its own meaning in terms of the units. So how do we do it? By again let's mathematically represent it. So let's compute the individual impact HI as the sum of the product of each flow which we computed previously and the corresponding characterization factor. So characterization factor is something that you multiply to convert them into the common footing. So for instance, HI would be sigma of j over a period of phi ij or rj. For each flow, you have to identify the characterization factor, and you do have to do a summation of the product. So you can again write this in terms of the matrix notation. H is equal to psi times R. So the matrix psi has rows representing the characterization factor of specific emission to the impact category. So this is how we capture this. So this is one. So we will see an example later. So the summary here is this matrix and equations typically allow systematic and consistent approach for quantifying the environmental impact. Okay, so how this environmental impacts have been what is this, why these are there? So this is due to the activities based on the specific contribution to different environmental concerns. For instance, that is acidification. One such characterization is acidification, and the other one is global warming potential, and we will see that in the coming slide. So these are commonly characterized or commonly known environmental impacts. For instance, we know that global warming is going to increase the temperature of the earth, and eventually relating to climate change. Acidification would have impact on soil, maybe acid rain, and so on and so forth. So so but all of these variables are in certain different forms. So we are doing is by step we are moving and converting to something that is an equivalent or something that is tangible. Okay, so let's take an example. Consider as life cycle emission of 10 kilogram CO2 of 2 kilogram CH4, 5 kilogram of SO2 and 3 kilogram of NO2. Convert these emissions to the global warming potentials and acidification potential. The characterization factors are 1 kilogram of CO2 equivalent per kilogram of CO2 is 25 kg, 25 kg CO2 equivalent per kilogram of CH4, 1 kilogram of SO2 equivalent SO2 equivalent per kilogram of SO2, 0.7 kilogram of SO2 equivalent per kilogram of NO2. These are the conversion factors. So now, so global warming potential is something that is concerning the CO2, while the acidification is potential is something that is concerning SO2. So how do we compute this character? How do we compute this again? So we look at the individual impacts H as the linear combination or the linear sum of each of the resources or resources and corresponding characterization factor. So how it becoming 1 times 10 because it is 10 kilogram of CO2, 10 times 1 or 1 times 10, how do you want to do it? Okay. So 25 kilogram of CO2 times 2. So then then 0 times 5 and 0 times 3. Why? Because SO2 and NO2 are not typically contributing to global warming. So while they are contributing to the acidification potential. So you put them 0 here and this would be equivalent to 16 kilogram of CO2 equivalent. So now similarly we let's compute the acidification potential. So first two components CO2 and CH4 typically not contributing to the acidification potential, while the other one, so 5 times 1 and 3 times 0.7. So this would be equivalent to 7.1 kilograms SO2 equivalent. So now we can also write. So these are linear equations. We shall be able to write this in the form of matrix. Okay, 1, 25, 0, 0. Okay, 0, 0, 1.7, and of course the variables are 10, 2, 5 and 3. This is what we are getting in a simple solution. We are getting here 60, 60 is 7.1, 7.1. This is a compact matrix notation. So these emissions are equivalent to, so what are we inferring? So these emissions are equivalent to 60 kilogram SO2 equivalent and 7.1 kilogram of CO2 equivalent. For emission flows are converted to now to impact flow, which is tangible. One is related to global warming, other one is related to acidification. You have now, see, now we don't have to work with CO2, CH4, SO2 and NO2, but we can quickly talk about something that is concerning global warming and something that's concerning acidification. Okay, so now we may have to, we have learned about allocation in the previous session. So we may have to do certain allocation. I'll tell you, so we'll look at the cases again. So look at a case of the same. So we have 50 liters of crude oil going inside, 1 kilogram hour of 1 kilowatt hour of electricity is also feed in. Okay, this would result in 20 liters of fuel and a byproduct worth 5 liters. And if you look in terms of the energy generation process, one of course, first one is the fuel production, because you say that the crude oil refining would also require certain energy. It is how do you operate your distillation column, that would result in that would require certain energy. Similarly, the energy generation, you will have to feed in this fuel. So it is very circular in nature. So electricity generation requires fuel and fuel production requires electricity. So 2 liters of fuel going in and it would be leading to X quantity of electricity and 10 kilowatt hour and corresponding emissions in both of these cases. So we may have to use displacement methods and allocation methods when so in fact specifically displacement methods if a single unit produces more than one product. So here there is more than one product and which essentially concerning more than one economic flow. So let's write it here. Okay, fine. So the fuel output is 20 liters. Okay, 20 liters, and fuel input here 2 liters. So 20 S1 minus S2 is F1. Okay, and this is concerning your byproduct 5 S1 is equal to F2. Okay, and the next is related to electricity minus 1. Okay, 10 and F3. We may be able to nicely represent this in terms of matrix form. So 20 minus 2, 5, 0, minus 1, 10, S1, S2, F1, F2, F3. Here F1, F2, S3 are economic flows of fuel, byproduct and electricity. S1 and S2 are the scaling factors or multiplier that of P1 and P2, which is concerning your production 1 and production 2. Okay. And now what is the problem? So now you can see that this is not this, you can't solve this equations. These equations cannot be solved unambiguously, because after specifying the final demands, we have 3 equations here and 2 unknowns. There are multiple solutions. So how do we fix this? So you will have to do certain allocation to fix this issue. So once we fix the allocation, we see that the number of equations and unknowns are fairly going to be the same. So now let's look at over here. How do we allocate or partition it? Allocation by partitioning requires splitting of the process with multiple products into multiple processes, each with a single product. So we have to look over here. This is a product having, it's a multi-component production system, which we now split into two processes having individual output. So let's see. And how do we do? Then we'll have to partition it. So let's try to partition it based on the output. So here you have 20 liters of fuel and 5 liters of byproduct. So we need to find out a fraction. That's what we have learned last time. So how do we look at the fraction? Let's say if you wanted to do this process from the from looking at the outputs. So we'll have to compute. So the total output can be 20 plus 25, 25. 20 by 25 gives you 0.8, which is the allocation factor for the component 1, and the remaining would be 0.2, which is like 5 by 25 or 1 minus 0.8, or what you wanted to say. So now you can say that whatever here it is written 40 liters is just by multiplying with this allocation factor. So you have to multiply 0.8 either of this or rather both of this. So you will see that this is the scale variation. So 50 become 40, 1 become 0.8, and so on and so forth. So similarly, so what we are, so what is remaining here? So what? So see, and so you have to do the full balance. So you have 40 liters of crude oil you have used, and what is remaining? So you actually create a sub process wherein we partition the remaining 10 liters of crude oil, and we just assume that they are going as an input, and remaining 2 kilowatt hour of 0.2 kilowatt of electricity. Fine, and that is yielding you the byproduct 5 liters. So output of this is like this. This is the 2 component output. Finally, the remainder has been transferred here for what you call bookkeeping. Fine. And for product 2, there is no problem because it is single output. So it is going 2 liters fuel and 10 kilowatt hour of output with desired emissions. So this is how we have to adjust our analysis. So we have to see that, so your emissions are also now equally distributed. This is 2 and this is 10. So this is 1.6, so it has to be 0.4, 8, it has to be 10. So now when we write this, you see that you have equal number of equations and equal number of unknown, because we have created a sub process here. So let's again rewrite 20 liters of fuel in S1A, S2, S1B. This, let's call it this process 1A, and this is process 1B. Fine. So and you kind of and we say that 2 liters of fuel is being consumed here. So 2002 is your first line corresponding to the fuel. Okay, and byproduct 5 comes out here, that is only one process, fine. So now 0.8 electricity is going inside here, okay, and similarly minus 0.2 electricity is going inside here, fine, and we are getting 10 kilowatt hour of electricity, which is the plus 10. So this now balanced in terms of the number of variables and number of equations. Similarly, if you write that in terms of the fuels, so minus, this is minus 40, minus 10, there is yes, so this is minus 40, minus 10, and that's all about it, okay. And so this is so this is, I'm talking about the environmental so the first one is all about what we call it as the economic flows, and the second one we call about we are talking about the one that is concerning environmental. So let's see so typically the economic flow and the environmental flow, which I am talking about the in the technology matrix and the intervention matrix. So let's write the intervention matrix at this moment. So you can see that 40 minus 10, both of them are input, emissions are outside, 1.6, okay, 0.4, 0.1. So you can see this over here, and you can have 8, 2 and 1, 8, 2 and 1, and this is the scaling factor corresponding to process 1A, process 1B, and of course the process 2, which is now the output would be given in terms of the resources of crude, SO2 and CO2. So now this is now fairly easy to handle. So now further, what have we done in this context? Okay, so the previous case of 20 minus 250 minus 110, if you go over here, this was the matrix. We nicely partitioned into this, right? Okay, 20, 0, 2, 0, 50, and the last row what you see here is 0.8 and 0.2 is coming is nothing but the values of this fractions which we computed. So you may say that this is W1A, W1B, and you have the negatives here, and this is the last term 10. And similarly for the environmental flow, you can see that minus 50, 10, 2.1, 10, 1 has become of this particular structure, because this was the original structure, fine. So this was the original structure, and eventually now it is now looking like this. So this is how we wanted. So this would eventually result in partitioning the matrix. So the Ws are the weight allocated to each of the sub process, fine, and eventually this would result in if there is no allocation is done, then we can say that by default this number now become 1. So now let's with this let's go ahead and do one more step of analysis, okay. So consider the generation of 100 kilowatt of electricity by the process, determine the life cycle force, perform the allocation by volume. So what would happen here? You are so the F1, F2 and F3. So the third is the electricity you are saying it is 100, fine, and rest all are acity. So F1 is equal to F2 is equal to 0, and we use them to solve this by means of this analysis, okay. And when we solve this, what we are going to get is we will get S1A, S1B and S2, which are the fractions, or rather the coefficients corresponding to these, and it happened to be 1.01, this is 0, and S2 is again 10.1. So now what we can do is we can now compute what is this number equivalent. So which essentially means that once we get this number, we will be able to now calculate what is the CO2 emission and SO2 emission corresponding to this, because now these numbers are available to us. You can just plug in. So 40 liters of crude, because S1 sorry. So yeah, so you see that your S1B is 0. So 40 liters of crude oil resource is being used, okay. Now you can see that 1.6 multiplied by S1A, which is close to 1, and S 0.1 times 10, which is like 1 plus 1.6 plus 1, close to 2.6 kilogram of CO2, and 8, this would be 8, and this is 0, and this is close to 10. So, 8 plus 10, close to 18 kilogram of SO2. So, here we nicely transformed this analysis and evaluated the equivalent of what we call as the acidification potential equivalent, which we corresponding to the, and also the CO2 equivalent, which is relating to the global warming potential. Or so now, so what we have done is partition and allocation. So now, if there are byproducts, and the byproduct, so see, the point is that when we are producing something and you are getting a byproduct, so it is not by desire, but the product is, so the process is giving you an additional product. So now, when we, how do we analyze this? So it is something that we were not really wanting it, but the process as part of its reaction is giving you this byproduct. So what you also have to do is also need to account for this additional thing. So you don't have to now additionally do a production for this byproduct, because this particular product, fuel production P1, is actually giving you this byproduct. So we also need to reduce the effect of individually making the product of this, because now this process is giving you this, you actually saved somewhere making of this process. So that thereby reducing the or rather eliminating the environmental and its economic flow. So we'll have to do that calculation also. So this is done by this is done by means of the displacement approach to account of the byproduct. It requires the data about the conventional process that produces each byproduct individually. The approach actually uses a byproducts in one process so that it can displace the output. That's why the term displacement comes in. Displacement output from the other process. The displacement is typically represented by running the conventional process in the opposite direction. So, let us say you are looking to produce 1 kilogram of this byproduct by means of some naturally benign process, wherein you use 50 kilogram biomass, 0.1 kilogram of SO2 and 0.3 kilogram of CO2. So, now what we have to do, we are getting 5 liters of this byproduct, which essentially means that you have to scale this up to 50. You may be using 250 kilogram of biomass, 0.5 kilo, and as a result 0.5 kilogram of CO2 and 1.5 kilogram of SO2 would have been produced. So eventually, what would have happened is you would have saved this emissions, right? Because this is now being saved, because you don't have to do this process individually to make this product, because your P1 is giving you this. So as a result, this is what it means. So how to account for this is by running this, you do this reverse calculation. So the opposite running indicate that the conventional process is reduced to or avoided due to the byproduct use. So then we have to do the same level of equations, or we have to adjust that by means of account, or rather adjust or account these in terms of the overall impacts calculation. So these impacts are calculated in terms of the resource use and emissions for the life cycle of the product. So I think this is what it is being summarized. So you have a byproduct and the generation system is fairly unchanged. So how to account for this now? Again, you will have 100 kilowatt hour of electricity. You have to account. These two are coming from your initial calculations, fine. So this is coming from the individual computations, and we have to compute the inverse to compute your corresponding S1, S2, S3, and it would now give you what is equivalent to this also we have learned. So how do you get S1 here? Is taking the inverse of this matrix. This would result in S1 is equal to 1, S2 is equal to 10, and S3 is equal to 5. So now you may use this over here. Here also the first two process is remain unchanged. It is coming from here. So it is coming from here, while the third process is where we have accounted for your emission. So that's why you see that there is a minus 0.1 and minus 0.3 comes in, because that is something that you have saved due to the production. That's the production savings due to the byproduct generation. Fine. So we can again plug in this S1, S2, S3 and correspondingly get your RCO, R crude, RCO2 and RCO2. So you can see that the emissions for a final demand of 100, electricity is found to be 2.5 kilogram of SO2, 18.5 kilogram of CO2. Additionally, a 50 kilogram of crude oil is additionally used. This calculation also indicates that the biomass use will decrease by 250 kg due to the displacement. Yes, that is another. So you will have to have this many biomass. So see, what is the advantage? So biomass is typically a waste, right? So when you so now that waste is now taken part in terms of the production process, thereby you are again being benign to the environment. So this is how we tend to go circular. So you have used something to generate something, wherein the first product is happen to be typically a waste quantity. And you can also see this. So this would be, the numbers are now 2.5 kilogram of SO2 here. So it is now fairly similar, and this is also 18.5 kilogram of CO2. So for 100 kilogram production of electricity compared to the individual cases. So this is how you account if you have a byproduct generation, because the byproduct generation has to be accounted by running the process in a reverse mode and computing the numbers appropriately. Okay, so now let's look at the input output analysis in lieu of the process network analysis. So we were looking at the process as a network going from here one point to one point, and this also we also looked at this concept in the previous session, and there is process network, input output network, and eventually a hybrid network. So we will not go into the detail, but let's look at how we do a similar analysis in an input output setting. Input output analysis address some of these shortcomings because it circumvents the need of the choose of the most important process by considering a group of processes within a large boundary that spans a selected geographical region. The computational and data challenges posed by large boundaries are managed by aggregating individual process of small scales. So look at this particular case, you have a sector 1 and a sector 2. Okay, when sector 1 is interacting with sector 2 and sector 2 is interacting with sector 1, and xij, which essentially x12 and x21 and x11 and x22 here represent the flow from sector 1 to sector I to the sector j, and sometimes within the sector also you may reuse the variable. So that's why x11 has a self loop, x22 has a self loop. And what is the final demand product is so we will have a final demand product, okay, either F2 or F1. So for a ith sector it is Fi. So for sector 1 it is F1, sector 2 it is F2. And the next term is VI. So every sector you will also adding value to each of the sector, and which is represented by VI, V1 in for sector 1 and V2 of sector 2. So value in the sense that it typically include labor, which is not part of the immediate transaction. So this is, so by doing a labor, what are you trying to? You are giving job to people, and eventually their livelihoods are getting benefited, and so on and so forth. And eventually what you have to do, we have to balance this entire thing. This is a very similar to a analysis, what we call it as system dynamics. So eventually you will have to balance this entire loop. The balance condition for each sector is given by the equation. So you have x11, x12 or whatever till x5, x1n, and of course the Fi should be equal to the value that is being produced, x1i, x1i plus x2i plus xni, okay, from another sector to the another sector. So, you see that the index got flipped here. Here I1 become 1i because both of them are interacting each other, and so when you do this, when you get a demand, it will also supply you a value. So, that value eventually you call them as x1. The equation means that the input and final demand for a sector must be equal to all outputs and value added in that sector. So, now how do we further analyze this? So, the one way is to again go to a mathematical framework. So, let us assume that you have quantities x1 to xn which represent the total flow, which we don't now which we do not categorize them specifically as input or output or throughout the entire sector. So, we say that A11 x1 plus A12 AI2 actually for an ith component, AI1 x1 plus AI2 x2, so on and so forth, plus Ai n xn plus Fi is equal to the xi, and we can now write them in a vector matrix form. All the A can be now aggregated as a big matrix A, all x1, x2, xn can be aggregated as a big variable x, and all F1 to Fi, F1 to Fn you can aggregate as an F, and all xi to xn you can aggregate as an x, where Aij is nothing but xij by x, which represents the flow between I and j per unit throughput from the sector j. So, nothing but these are nothing but the normalize the flow. So, we really don't know. Sometimes the transaction in one directional may be in the order of thousands, while the reverse transaction may be of the order of maybe hundreds. But if you wanted to bring into the same footing, you will have to do this, what we call it as the normalized transaction, which is done by computing the division of xij minus xj, which is typically indicating the flow between sector per unit of throughput. So, once we have such linear algebraic equation, it is fairly easy to solve. So, the key aspect again what we need to look into that. So, your Aij are constant for a given system, means if the throughput xi for a sector, if a throughput xi for a throughput xj for a sector changes, then the flows of the sector xij change in proportional to the change. So, we assume that things are happening proportionately or linearly, which may not be true in reality, but for this particular analysis we need this. That's why we say that some of these assumptions might include model uncertainty, which again part of your LC analysis. So, this would be now I. So, if you take x x ai x this side, I minus ai naught x times f, so x would be I minus ai naught inverse time f. This particular factor, which is known as Leontief inverse or total requirement matrix, which can also be represented. So, this is a plus b raised to minus 1 kind of a structure, which is forms a power series. So, power series you can of course expand and write. One way to write it like 1 I, this is I naught I 1, it is I identity matrix I plus ai naught square, and so on and so forth. You can write them as a infinite series, and you may truncate at any point that you would like to. So, again let us look at a simple example. How do we implement this? So, let's look at a network. So, there is two units that is interacting to each other. So you can see this directionality and the interaction values in terms of the connection. So, let's now try to create this framework. So, for a given network, determine the direct and indirect total direct and total requirement matrices, calculate each term of the infinite series expansion and interpret its contribution to the throughput. Note that the flows are inconsistent unit, which may be monetary or physical. We don't need to worry about, we don't need to physically split them. They are all in the consistent unit. The 100 here means it is equivalent to 150 here in terms of the unit, not in terms of the value. So, look at here. So A11, okay, there is you have to do a calculation, right? Ratio of this to this. So there is no, it's just there is nothing in there is no unit transaction, would be n1 is equal to 0. Now look at A21, okay. 50 is going back, 150 is coming in, so 50 by 150. Now A12, okay, so 100, 150 coming in, 150 going out, 100 plus 50, 150 coming in, 150 is going out. So this interaction value is 2, is 1, and similarly for A22 there is no interaction, so it would be 0. So 2 is not support. So if you see a self loop here and if you see a self loop here, you may see these numbers are non-zero, but at the moment there are not there. So your A matrix, you now compute it as 0, 1, 1 by 3 and 0. This is what it is written over here. Then we compute the length inverse I minus ai naught is equal to inverse, you will get it. And what we need to look here is if the final demand from the process 1 is 0 and the final demand from the process 2 is 100, we can write the f value. It's of course not given. Let's assume that these are the numbers 0 and 100. Fine. Then your x would be this inverse times this so inverse times this number. So inverse, of course, you can write it as the infinite series. Okay. So then what we are going to get here is, okay, is I times your f, a times f, a square times f, and so on and so forth. And you, what you are going to get here, I times f is of course f, which is nothing but the final demand. Okay. Now the second one, it is the term that if that is that shows the effect of the final demand with the flow from the sector 1 to match the flow of the sector 2, and the third term is the effect of the second term through the recycle stream, okay, and so on and so forth. Eventually you can of course compute it, and eventually you will get a value which is corresponding to the final x. So now look at a slightly extended version of this particular input out model, which we call it as environmentally extended input output model. The basic input output model is what we have learned. It only represents the economic flows between the sectors in terms of monetary benefits, right? But these are useful for assessing the environmental impact when combined with the environmental interaction data. So how do we do it in this context? So which we call it as EEIO models, which incorporate the environmental data with economic transactions. They allow for the assessment of both direct and indirect environmental effects of the economic activity. So what we do, the direct inputs from the environment, you call them as MIJ, which we show in the this dashed arrows. So these represent the input from an environment to the sector. So these are all going inside, you see, from a sector. For example, these could be water, coal, maybe air, and so on and so forth. For instance, you may so you may capture air for certain process. That's something coming from environment. So you can accommodate all of them. So again, how do we do this calculation? So how to, and eventually there would be emissions to the environment. So emissions are typically represented by I with subscript ij indicating the emission from the sector I to the environment. So we may be able to do again the linear combination based analysis like last time. Mi is equal to sigma j ri j xj, ij is equal to qij times xi, m is times of rx, l is q transpose x, and we can again compute r star, which is in terms of the Lentef inverse, r times I minus a inverse. Here q times iq transpose, it is actually I minus a inverse, and you can compute m and l. So when we computed q and r, it would be r times f, q times f. So similar analysis, but slightly more complicated setting, where we also include the environmental effects. So now that is done, we are ready to discuss regarding the carbon footprint. And now we are ready to quantify the footprints assessments. So so there are multiple footprints possible. So one is of course the carbon footprint. What is let's start with the concept of footprint in sustainability. Footprint represents the direct and indirect environmental impact of impact of an activity. It is typically measured as a single unit for simplicity and focus on significant environmental change. We will not look for smaller effect. So if there was a temperature change or a heat wave happen at one particular place for one particular time, we don't care. But let's say if it is consistent and it is significant, then we include. And for and typically popularity of the environment footprint approach is favored by its straightforward methodology, because the calculation is fairly straightforward and it eventually addresses the pressing environmental issues related to two important environmental issues. We will see that later, which is something related to climate change and water scarcity. So now you also need to account when we talk about climate change and fresh water or water, you have to look for a planet wide analysis. So then we'll also have to look for the footprint method if eventually used to measure the consumption against Earth's ability to regenerate the resources and absorb waste. And what is the fundamental here? The fundamental analysis is rooted on the fact that uh, on anthropogenic climate change, the emissions of the greenhouse gases and their increasing concentrates in the atmosphere is what it is raising the concern. The key variable that affect this is methane, nitrous oxide, CFCs and HCFCs. And what does the recent trend say? CO2 and N2O levels has been rising, mainly due to the fossil fuel and industrial processes. CFC concentration are declining because now there are bans related to usage of certain gases that eventually result in terms of reduction in terms of the international effect, and of course HCFC and methane concentration continue to increase. So how do we compute the global warming potential? So global warming potential, yeah, so each greenhouse gas so see so when we work with gases, every gas would have a different correspondent to global warming potential. So each greenhouse gas has different contribution to a radioactive forcing. Greenhouse gases are compared with the global warming potential in CO2 equivalents, as we all see here, and GWP, global warming potential, okay, is a measure of how much the emissions of 1 ton of a gas will absorb over a period relative to the emissions of 1 ton of carbon dioxide. Global warming potential thus compares the ability of each greenhouse gas to trap heat in the atmospheric related to CO2. Over 100 years inter-year period, methane, it's observed that the methane has become 25 times more potent than CO2, and nitrous oxide has become 298 more potent. The potency of these gases changes over time because uh, the environment characteristics changes over time depending upon their lifespan and atmospheric properties and other factors. In 2016, it has been observed that atmospheric CO2 equivalent were reported is 489 parts per million, and aggregation of all of this is done using in terms of the global warming potential of each of this. So the global warming potential of the jth greenhouse gas multiplied by its mass summed up over a period of time. So this is some of the table typically shows some of these gases and its global warming potential: carbon dioxide, methane, nitrous oxide, CFC11, carbon tetrachloride, HCFC, HFC, sulfur hexafluoride, and methyl hydrochloride. Then its their chemical formula. It is all evaluated in terms of CO2 equivalent. Since the basis of the CO2 is 1, and what we see here is 20 or over a period of 20-year time, the greenhouse gas potential of methane is 72 times more than carbon dioxide, and if it is sulfur hexafluoride, it is 16,300 times more potent than carbon dioxide. So now let's look at how of these are computed. So life cycle inventory. So let's say if the life cycle inventory of a process consists of the following emissions, which is 20 kilogram of CO2, 0.001 kilogram of CFC11, 0.5 kilogram of N2O, and 2 kilogram of NO2. How do we compute? 20 kilogram of CO2 would be as it is because that's the basis. CFC11 is 0.001 kilogram over a period of 100. So we have to go to this 100-year table of that particular column, and CFC11 is 4750 times 0.001. And similarly, it is 0.5 times N2O. So N2O is nitrous oxide, and it is 298 times 0.5, and you see that the summation of that, and we deliberately see that sorry, NO2, right? It is NO2 has excluded because NO2 is typically not contributing to global warming. So now see how do we standardize all of this. So there are three scopes in standardizing carbon footprint, one relating to direct emission, and the second relating to emissions from heating and electricity generation, and third coming from all emissions from the entire cycle. And what is scope 1? Okay, scope 1 essentially means that this is the most immediate and direct impact, okay, impact of greenhouse gas emissions calculation, focusing on the emissions from selected processes that are directly produced by the reporting entity. This could be, for instance, emission from a manufacturing process, company-owned vehicles, and so on and so forth. This is the direct case. Second is the emission from heating and electricity generation. Here, a scope widens the boundary to include the indirect greenhouse gas emission associated with generation or purchased utilities like steam, steam, heat, cooling, electricity, and so on and so forth. This entity doesn't fall direct that these entities doesn't generally emit as greenhouse gases, but they result from the entity's energy consumption. So if you buy something, that's why electric vehicle analysis, we say that electric vehicle do not pollute environment. That's of course not, it's a very relative statement in that sense. Why? Because there are ways in which you are consuming electricity, so wherein you have actually utilized some means to generate some of these emissions. The components of the electric vehicle is also manufactured by some means where you have consumed electricity, wherein you have already done some direct emission. And the last is the scope 3, where emissions from the entire life cycle. This is the most comprehensive scope encompassing the all direct and indirect emissions that occur directly with the entity's value chain, including the both upstream and downstream emissions. This includes the full life cycle of product, from raw materials acquisition through end of life disposal. It also captures the wider impacts of an entity's operation, such as business travel, investment, and waste disposal, and so on and so forth. So the next important footprint is water footprint. What is water footprint? Water footprint offers insights to the direct and indirect use of the water for the product and process and system. So this is particularly important since many of the process activity requires water, and most of this world's uh, such regimes are severely water stressed. So then how do you quantify it? There is four ways in which you quantify the water footprint. But one is called virtual water. Virtual water is the total volume of the water that is used to produce the product or service, including both water embedded in the product and the water that cannot be reused for any other purpose. It's a key component of the water footprint that include water used throughout the entire life cycle of a product or service. For example, virtual water in a beverage is the water contained in the drink itself, which because you can send it back because you are going to drink it, while the virtual water in thermal power generation include the evaporative losses because you won't be able to regenerate the evaporative losses and water used in various stages of the process. And what is blue water? Blue water, it covers the fresh water, it covers the fresh water use that is available on the surface as groundwater. It is essentially the water extracted from rivers, lake, aquifers, etc. for human use. And grey water refers to water from precipitation that is absorbed by soil and used by the plant. It does not run off or recharge aquifers, okay, because it is just directly going into the soil. This type of water is mostly used for agriculture and forestry. And the last is what we call it as the grey water, okay. Grey water is about not about the water type, it's about the water quality. It is pertaining to the fresh water that is required to assimilate a lot of pollutant so that the quality standards can be achieved. The water footprint or the grey water footprint is typically calculated by considering the volume of the water that is needed to dilute the pollutants to an acceptable level, which can typically be represented by this equation as a ratio of P into Cmax and Cnat. So, P is the load of pollutant, of course, in terms of the flux mass by time, okay, and Cmax is the maximum allowable concentration and Cnat is the natural concentration of the pollutant, and gray is the water. So, you have a pollutant load and we add the gray water at the natural concentration and eventually would leading to water that can uh, sustain or rather the maximum concentration. So, how do we compute a water footprint? So, let us look at an example. The production of 1 kilogram of product E withdraws 200 liters of water from a river and returns 150 liters of at a downstream location. The manufacture of 1 kilogram of the product also requires 0.2 kilogram of A, 5 kilogram of B and 1 kilogram of C. These resources A, B, C uses 10, 100, 10 and 80 liters of water per kilogram respectively. Determine the virtual water that is required for making 1 kilogram of E and its water footprint. So, virtual water is the water that is direct water, right? It is used for in itself. So, it withdraws 200 liters and returns 50 liters. So, virtual water would be 200 minus 50, 150, which is 50. The footprint of a water footprint analysis, you will have to look for direct and indirect usage. So, we may define a boundary that include resources A and B needed to make the product E, but ignore the activities beyond this. Then the water footprint of E may be calculated as, of course, 50, which is the blue, which is the virtual water, okay, and 0.2 times 100, 5 times 10 and 1 times 80. This is the total water footprint or water requirement or whatever you want to say, water footprint of E. So, you have to say that it uses 200 liters. It essentially means as a water footprint of E. So, now you are quantifying or now plotting it against a product. So, water footprint of E is now 200 liters of water. Okay, so now let us compare the carbon footprint and water footprint in a slightly larger scale. So, how it affecting ecosystem services? Carbon footprint focus on how the activities impact on carbon sequestration and measured in CO2 emission, and water footprint concentrate on the impact of water by professional services, of course quantified by the volume of the water consumption. And supply, it doesn't, carbon footprint doesn't take care the supply ecosystem capacity to provide the services related to carbon sequestration, and it does not evaluate ecosystem capacity to supply water related services. Spatial scale can be applied across different geographic scale as detailed by network analysis methods, which is of course discussed before. And in terms of water footprint, it is adaptable to various spatial scales with network analysis and techniques, which is again discussed previously. Temporal dynamics, how it is, so see, you have to look how it is, your water footprint calculation is spread across a geographical area, which is talking about the spatial scale and how it is varying across time. over a period of time, where we talk about the temporal dynamics. In temporal dynamics, this lacks consideration for changing condition over a time that can affect the carbon storage of emission. And in water footprint, it omits the dynamic temporal variance in water use and availability. Interdisciplinary effect, carbon footprint typically do not include interdisciplinary effect. Doesn't include the influence of footprint reduction and decision across various disciplines. Again, it also does not, in water footprint calculation, also does not assess the broader impacts of decisions aimed at reducing water use of different disciplines. And flow types provides a single measurement focus, thereby not accounting multiple types of flows other than carbon emission. And water footprints aim to provide a singular measure, not accounting for varied types of water flows except for consumption. So, with this we summarize this lecture. So, we use some of these concepts in terms of the analysis at later time when we do a sustainable design. So, summary here is process network analysis includes systematic methods to construct life cycle network and connects models of individual units. Mathematical framework is used to model complex interaction between economic and environmental flows for a specific consumption of product, society or final demand. The resource consumption and emission may be calculated by R is equal to B inverse S. One is technology and one is related to consumer activities, and other one is related to economic activities and emissions, environmental flows, economic flows and environmental flows. The characterization factor converts the environmental flows to measurable environmental impact to facilitate the comparison of different environmental impact by converting to a common unit. In case of multiple products from a single process, extended network analysis is required for utilizing the allocated or displacement methods. Input-output analysis addresses the shortcomings of process network analysis. It circumvents the need to choose the most important process by considering the groups of process within a large boundary that spans over a selected geographical region. Basic input-output model represent economic flows between sectors in monetary terms. They are useful for assessing environmental impacts when combined with environmental interaction data. Environmentally extended IO models, input-output models, incorporate environmental data with economic transactions. They allow the assessment of both direct and indirect environmental effects of economic activities. And the last is carbon footprint and water footprint. Carbon footprint quantifies the total greenhouse gas emissions caused by directly and indirectly by an individual, organization, event or a product, while a water footprint measures the total volume of fresh water used to produce goods, services consumed by the individual, community or produced by a business. With this we conclude this session. Thank you. We will continue the lectures that takes care some of this principle, how do we do a further quantitative analysis. Until then, bye. Thank you.